When we think about cold, most of us imagine something familiar. Maybe the feeling of stepping outside on a winter morning. The air is sharp, your breath becomes visible, your hands begin to sting if you forget your gloves. Or perhaps you picture opening a freezer. The cold air spills out like a quiet cloud, and you can feel it immediately against your skin. Cold in everyday life always seems connected to air. The wind makes it feel colder. Snow covers the ground. Ice forms on lakes and windows. But space is very different. Out there is almost no air at all. So that raises an interesting question. If space is a vacuum, if it's almost completely empty, then what does cold even mean there? To understand that, we need to think about what temperature really is. Temperature is not actually about how something feels, it's about motion. At the smallest level, everything around us is made of tiny particles, called atoms and molecules. These particles are always moving. They vibrate, spin, and bounce into each other constantly. When something is warm, those particles are moving quickly. When something is cold, they move more slowly. Imagine a crowded dance floor at a party. Music is loud. People are moving everywhere, bumping into each other, laughing and spinning around. That's like warm matter. Everything is energetic and active. Now imagine the music slowly fading away. People stop dancing. The room becomes quiet. Movement slows down. That's what happens as temperature drops. The colder something becomes, the slower the motion of its atoms. In fact, scientists have discovered that there is a theoretical limit to how slow atoms can move. The slowest possible motion happens at something called absolute zero, which we'll explore later in our journey. At that point, atoms are almost completely still. But here's where things become interesting. On Earth, temperature usually spreads through air, water, or solid materials. If you hold a hot mug of tea, the heat travels through the mug and warms your hands. If you step outside in winter, the cold air pulls heat away from your body. But space has almost none of that. There is no thick atmosphere floating between objects, no air drifting from one place to another. Most of the universe is closer to an enormous empty room than anything we experience on Earth. So how does temperature work in a place that is mostly empty? The answer involves something subtle but powerful: radiation. Every object that has any temperature at all gives off energy in the form of light. Sometimes that light is visible, but often it is invisible radiation like infrared. You can think of it like a gentle glow. Even your own body is quietly glowing in infrared light right now, releasing warmth into the room around you. In space, this glowing energy becomes the main way heat moves around. Without air or water to carry warmth, objects slowly gain or lose heat by absorbing or releasing radiation. Imagine standing alone in a vast empty desert at night. No wind, no clouds, no buildings nearby. Your body would slowly release heat into the dark sky. Now imagine that same idea, but expanded to the scale of the universe. That's how temperature works in space. Objects slowly exchange energy through radiation, quietly glowing into the darkness. Because of this, space behaves differently from what many people expect. A common myth is that space instantly freezes everything. You might have seen this idea in movies, where someone steps into space and turns into ice within seconds. But that's not actually how it works. Without air to carry heat away quickly, freezing in space would happen more slowly than people imagine. In fact, if you were standing in direct sunlight in space, the sunlight could warm you quite strongly. That might sound strange at first. How can space be both extremely cold and yet able to heat things up? The key is sunlight. Near Earth, the sun shines with incredible energy. The sunlight hitting our planet carries enough warmth to keep oceans liquid and forests growing. If you were floating near Earth in space, the side of you facing the sun could become very hot. Meanwhile, the side facing away from the sun would lose heat rapidly into the darkness. It would feel like standing next to a campfire on a freezing night. One side of your body warm, the other side cold. Except in space, the contrast can be much more extreme. But when we talk about the temperature of space itself, we usually mean something slightly different. We are asking, if you removed stars, planets, and sunlight, what temperature would the empty universe settle at? That quiet background temperature is astonishingly cold, so cold that it's only a few degrees above absolute zero. To picture that, imagine the coldest winter day you've ever experienced, maybe -10 degrees Celsius. Now imagine something more extreme, like Antarctica during its harshest storms, where temperatures can drop below -80 degrees Celsius. That already feels unbelievably cold, but the natural temperature of space is far colder than that. If Antarctica is like standing in a deep freezer, space is more like being inside a freezer that has been left open in the middle of the night on an icy planet. And even that comparison still doesn't fully capture it. The truth is that cold in the universe exists on a scale that feels almost impossible to imagine. The warmth we feel from the sun, from fireplaces, from warm rooms and summer days, these are small pockets of energy in an otherwise quiet and frozen cosmos. And that leads to another question. If space is so cold, why did the universe end up this way in the first place? To answer that, we need to travel back to the very beginning of the universe itself, when everything was far hotter than anything we experience today. Because strangely enough, the cold universe we see now began as something unimaginably hot. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. Long before stars, planets, or galaxies existed, the universe was a very different place. Instead of darkness and cold, everything was filled with intense heat and light. The entire universe was packed into a tiny space, far smaller than the distance between cities on Earth. Imagine squeezing every ocean, mountain, planet, and star into something smaller than a grain of sand. That gives a rough idea of how dense the early universe was. And when matter is squeezed that tightly together, something interesting happens. It becomes extremely hot. This moment is often called the Big Bang, but that name can be a little misleading. Many people imagine it as a giant explosion, like a bomb going off in space. But that's not really accurate. It wasn't an explosion in space. It was the rapid expansion of space itself, everywhere, stretched outward at the same time. If you want a simple way to picture it, imagine a balloon with small dots drawn all over its surface. As you blow air into the balloon, the surface stretches. The dots move away from each other in every direction. No single dot is the center. Every dot sees all the others drifting farther away. The universe expanded in a similar way, but instead of a balloon growing from the size of your hand to the size of a beach ball, the universe expanded from something incredibly tiny to something billions of light years across. A light year, by the way, is the distance light travels in 1 year. Light moves incredibly fast, about 300,000 kilometers per second, which is fast enough to circle Earth about 7 times in a single second. So when we say the universe spans billions of light years, we're talking about distances so huge that even light takes billions of years to cross them. But in the beginning, everything was packed together. The universe was like a glowing furnace filled with energy. Temperatures were unbelievably high, so high that atoms could not even form yet. Particles were crashing into each other constantly, moving so fast that stable matter simply couldn't settle down. If you imagine water boiling in a pot, bubbles rising and bursting everywhere, that chaotic motion gives a small hint of what the early universe was like. Except instead of boiling water, it was a sea of energy, hotter than the center of any star. So what changed? Why is the universe cold now instead of blazing hot? The answer comes down to something very simple: expansion. When something expands, it spreads its energy over a larger space. Think about a small room with a heater running. If the room is tiny, maybe the size of a closet, the warmth builds up quickly. But imagine removing the walls and letting that heat spread across an entire football field. Suddenly the warmth becomes thin and weak. The same amount of heat now covers a much larger area. The universe followed a similar process. As space expanded, energy became more spread out. Temperatures slowly dropped, minute by minute, year by year, millions of years passing quietly. At first, the universe cooled enough for particles to combine into simple atoms like hydrogen and helium. Later, gravity gathered these atoms together into the first stars. Inside those stars, new elements formed: oxygen, carbon, iron, the ingredients that would one day build planets and living things. But outside of those stars, the universe kept expanding, and with each passing billion years, the background temperature of the cosmos continued to fall. Imagine pouring hot tea into a massive swimming pool. At first, the tea is steaming, but as it mixes with the huge volume of water, the heat spreads out until it becomes barely noticeable. The universe experienced something like that, but on a scale beyond imagination. The warmth of the early universe slowly diluted as space grew larger and larger. Today, the universe is roughly 13.8 billion years old. If that timeline were compressed into a single 24-hour day, the Big Bang would happen right at midnight. Stars would begin forming during the early morning hours. Our solar system would appear very late in the evening, and human civilization would emerge during the final fraction of a second before midnight. Throughout almost that entire day, the universe has been cooling. Every moment, space stretches a little more. Galaxies drift farther apart. Energy spreads thinner, and the average temperature of the cosmos continues its slow decline. This leads to a surprising realization. Cold is not rare in the universe. Cold is actually the natural state of the universe. Warm places, like the surface of Earth, the glowing interior of stars, or the heat around black holes, are exceptions. They are small islands of warmth scattered inside a vast ocean of cold. Imagine standing on a tiny campfire-lit island in the middle of a massive frozen sea. That's a bit like our situation in the universe. Our sun keeps Earth warm. Without it, our planet would quickly cool to temperatures far below anything humans could survive. But the moment you move far enough away from stars and galaxies, the natural cold of the universe returns. And that cold is incredibly deep, so deep that the temperature of most empty space is only a few degrees above absolute zero. But where does that remaining warmth come from? If the universe has been cooling for billions of years, why isn't space already at the coldest possible temperature? The answer lies in a faint glow that fills the entire cosmos, a quiet echo from the birth of the universe itself. Even today, long after the early fireball cooled, a tiny trace of that ancient heat still remains, and it surrounds us everywhere. If you could travel far away from stars, planets, and galaxies, far beyond the warmth of sunlight, what temperature would you find? Imagine drifting into a region of space so empty that there are almost no atoms around you, no nearby stars shining light, no planets reflecting warmth, just darkness stretching in every direction. What would the temperature be there? You might guess that such a place would be completely frozen, reaching the coldest possible temperature in nature. But interestingly, that is not quite true. Even the emptiest regions of space still have a tiny bit of warmth. Today, scientists measure the natural background temperature of the universe at about 2.7 Kelvin. That number might not mean much at first, so let's make it easier to picture. On the temperature scale most people use, water freezes at 0 degrees Celsius. But the Kelvin scale starts much lower, absolute zero. The coldest possible temperature where atoms nearly stop moving is minus 273 degrees Celsius. So when we say space is 2.7 Kelvin, that means it is about minus 270 degrees Celsius. To imagine that, think of the coldest winter day you have ever experienced. Even in extremely cold places like Siberia or Antarctica, temperatures might reach around minus 60 degrees Celsius during severe storms. That already feels painfully cold. Now imagine something more than 4 times colder than that. That is the quiet chill of empty space. But here's the strange part. Why isn't empty space even colder? If the universe has been cooling for billions of years, why does it still sit at 2.7 Kelvin instead of reaching absolute zero? The answer comes from something incredibly ancient, a faint glow that fills the entire universe. Even though space often looks completely dark, it is actually filled with a very weak form of light. This light is so faint that our eyes cannot see it, but special instruments can detect it. You can think of it as a soft background warmth left over from the earliest moments of the universe. Imagine walking into a large room hours after a fireplace has gone out. The flames are gone, the logs are cold, but the room still holds a gentle warmth from the fire that once burned there. The universe is similar. The intense heat from its early beginning has faded, but a small trace remains. That leftover warmth fills every corner of space. It gently warms the universe just enough to keep it from reaching absolute zero. Another way to picture this is to imagine standing in the middle of a huge frozen desert. The night sky is clear and black. The ground is covered in ice. But somewhere far away, beyond the horizon, there are faint lights glowing softly. They are so distant that they barely warm you at all, but their presence keeps the darkness from being completely cold. The universe carries that kind of distant glow everywhere, and because it fills all of space evenly, it sets the natural temperature of the cosmos. Wherever you go, between stars, between galaxies, or even in the vast emptiness, far from everything, the temperature settles close to that same value. About 2.7 Kelvin. It is like the universe has its own gentle thermostat, a quiet baseline temperature that exists almost everywhere. But something else makes this even more fascinating. Space is not truly empty. Even the emptiest regions still contain a few particles drifting through the darkness. Sometimes just 1 atom per cubic meter. To compare that with something familiar, imagine a large moving truck filled with air. Inside that truck, there would be roughly 30 sextillion atoms. Now imagine removing almost every single one of them, until only 1 atom remains floating in the entire truck. That is roughly how empty interstellar space can be. Because there are so few atoms, very little heat can be stored or transferred. Temperature becomes a quiet background property, rather than something you feel. On Earth, cold air can bite your skin because billions of air molecules collide with you every second, carrying heat away from your body. In space, those collisions barely happen. Instead, objects slowly lose heat by glowing radiation into the darkness. A spacecraft drifting far from the sun, for example, gradually cools down as it releases infrared energy, but it will never cool much below that 2.7 Kelvin background, because the faint glow of the universe itself is always there. Now here's an interesting question. If empty space has a temperature of about minus 270 degrees Celsius, does that mean every object in space eventually becomes that cold? Not necessarily. Objects near stars receive energy from starlight. Planets absorb sunlight during the day and release heat at night. Even distant clouds of gas can warm slightly when nearby stars shine on them. But if something drifts far enough away from any source of heat, the background temperature of the universe becomes its natural resting point. That's why scientists sometimes describe space as a cosmic refrigerator. Given enough time and distance from stars, most objects slowly cool toward that same deep chill. And yet, surprisingly, there are places in the universe that are even colder than this natural background. Places where gas expands so rapidly that it cools beyond the normal temperature of space itself. That might sound impossible at first. How could something become colder than the universe around it? But nature has some surprising ways of doing exactly that. And one of those places exists inside a strange and beautiful cloud of gas, many thousands of light years away. If you could somehow turn your eyes into instruments that detect invisible light, the universe would suddenly look very different. Instead of pure darkness between the stars, you would see a faint glow surrounding you in every direction. It would not shine like a bright lamp or a star. Instead, it would be more like a gentle fog of light spread across the sky. Soft, even, quiet. No matter where you looked, left, right, above or behind you, the glow would be almost exactly the same. This faint light is known as the cosmic microwave background, often shortened to the CMB, and it is one of the most remarkable discoveries in modern astronomy, because this light is not coming from stars. It is not coming from planets or dust clouds. This light is the oldest light in the entire universe. In fact, it began its journey nearly 13.8 billion years ago, long before Earth existed, long before the Sun formed, long before the Milky Way even looked the way it does today. To picture how ancient that is, imagine the entire history of Earth compressed into 1 year. Dinosaurs would appear around mid-December. The extinction that wiped them out would happen around December 26. Modern humans would appear just minutes before midnight on December 31st, and this ancient light from the early universe would still be older than all of it. So where did it come from? To understand that, we need to go back to a time when the universe was much younger. After the Big Bang, the universe was incredibly hot and dense. It was filled with glowing particles moving wildly in every direction. Light existed everywhere, but it couldn't travel very far. Why? Because particles were constantly bumping into it. Imagine trying to shine a flashlight through a thick fog. The light scatters everywhere, bouncing off tiny droplets. It becomes impossible to see far. The early universe was similar to that fog, but instead of water droplets, it was filled with fast-moving particles. Light kept crashing into them. So even though the universe was glowing brightly, the light was trapped in a kind of dense cosmic mist. But as the universe expanded and cooled, something important happened. Particles slowed down. Eventually, simple atoms formed, mostly hydrogen and helium. Once atoms formed, there were far fewer loose particles floating around to scatter light. Suddenly, light could travel freely across space. It was like the fog lifting from a landscape after sunrise. For the first time, the universe became transparent, and the light that had been trapped before was finally able to move outward in every direction. That light has been traveling through space ever since, across billions of years, across unimaginable distances. And today, a tiny portion of that ancient light is still reaching us. But something interesting happened during its long journey. As the universe expanded, the light stretched. Its wavelength became longer and longer, like a rubber band being slowly pulled apart. Originally, that light was very energetic, more like bright visible light, or even stronger. But after billions of years of stretching, it has shifted into a much weaker form of radiation called microwaves. That's why scientists call it the cosmic microwave background. It is the cooled, stretched echo of the universe's earliest light. And it fills the entire cosmos. Every direction we look, it's there. If you pointed a microwave detector anywhere in the sky, whether toward a galaxy or toward a dark, empty region, you would still detect that faint glow. It surrounds us like a quiet cosmic ocean. Now here's something that might surprise you. The temperature of this ancient glow is exactly what we talked about earlier, about 2.7 Kelvin, or roughly minus 270 degrees Celsius. That faint microwave radiation gently warms the universe, just enough to prevent it from reaching absolute zero. Without it, space would likely be even colder. You can think of the cosmic microwave background like the fading warmth of a fire that burned long ago. The flames are gone, the sparks are gone, but the last traces of heat are still drifting through the air. The universe still carries the memory of its fiery beginning. But how did scientists discover this ancient light? Interestingly, it was found by accident. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working with a large antenna in New Jersey. They were studying radio signals from space, but no matter where they pointed their antenna, they kept detecting a strange background noise. At first, they thought something was wrong with their equipment. They checked everything. They cleaned the antenna. They even removed pigeons that had been nesting inside it, along with the mess the birds had left behind. But the noise remained. It came from every direction equally. Eventually, they realized something remarkable. The signal wasn't coming from Earth. It wasn't coming from the sun. It wasn't coming from nearby stars. It was coming from the universe itself. They had accidentally discovered the faint glow of the Big Bang, the oldest light in existence. Today, satellites have mapped this background radiation across the entire sky, and the maps reveal something fascinating. The temperature of this glow is almost perfectly uniform everywhere. Almost. Tiny variations exist. Differences smaller than 100,000th of a degree. That's like measuring the temperature of an entire ocean and finding differences smaller than a drop of warm water. Those tiny temperature variations eventually helped gravity gather matter together into galaxies and stars. But the overall background remained extremely cold. So when we say that the universe has a natural temperature of about 2.7 Kelvin, what we are really describing is the gentle warmth of this ancient cosmic light, the afterglow of creation itself. And yet, even within this already freezing universe, some places manage to become even colder. In fact, astronomers have discovered a strange cloud of gas where the temperature drops below the background temperature of space itself, a place so cold that it briefly became the coldest known natural object in the entire universe. When we look up at the night sky, it can seem as if the universe is filled with stars. Thousands of small points of light appear scattered across the darkness. With telescopes, we can see even more. Clouds of stars, glowing nebulae, distant galaxies shaped like spirals or glowing ovals. But this view can be a little misleading. The universe is not mostly made of stars. In fact, the overwhelming majority of the universe is empty space. Even inside our own galaxy, the Milky Way, stars are spread incredibly far apart. The nearest star to our Sun is about 4.2 light-years away. If the Sun were the size of a small orange sitting on a table, the nearest star would be another orange sitting thousands of kilometers away. That's already a huge distance. But the space between galaxies is far emptier still. Galaxies themselves are like glowing islands in an enormous cosmic ocean, and the water of that ocean, the space between them, is almost completely empty. Imagine standing on a small island, surrounded by a vast dark sea that stretches far beyond the horizon. Now imagine that the nearest island is not a few kilometers away, but millions of kilometers away. That begins to hint at what intergalactic space is like. The Milky Way galaxy, where our solar system lives, is about 100,000 light-years wide. If you could travel across it at the speed of light, the fastest speed possible, it would still take 100,000 years to cross from one side to the other. Yet even that enormous galaxy is separated from its neighbors by even greater distances. The nearest large galaxy, called Andromeda, sits about 2.5 million light-years away. To picture that distance, imagine shrinking the Milky Way galaxy down to the size of a dinner plate. In that scale model, the Andromeda galaxy would be another dinner plate placed about 2 meters away across the room. Everything between those two plates would be mostly empty. That emptiness is what astronomers call intergalactic space. So what is the temperature out there? Without stars nearby, without dense clouds of gas, without much matter at all. These regions settle extremely close to the background temperature of the universe, about 2.7 Kelvin, or roughly minus 270 degrees Celsius. That's colder than any natural environment on Earth by a huge margin. But temperature in intergalactic space behaves differently from cold environments on our planet. On Earth, when we say something is cold, it usually means heat is being pulled away from us by air or water. If you jump into icy water, for example, your body loses heat very quickly because trillions of water molecules are touching your skin and carrying energy away. In intergalactic space, almost no particles exist to do that. You might travel through millions of kilometers of space without encountering even a single atom. Imagine driving across an entire country and only seeing one grain of sand during the entire journey. That gives a rough idea of how sparse matter can be out there. Because of this extreme emptiness, the temperature of intergalactic space is more like a quiet background condition, rather than something that actively freezes objects. Objects lose heat slowly through radiation, rather than through direct contact. A spacecraft drifting far between galaxies would gradually cool down as it releases its own heat into the darkness. But the process would take time, hours, days, or even longer depending on the object. Still, eventually, most objects left alone in these regions would settle close to that same cosmic temperature, around 2.7 Kelvin. What makes intergalactic space particularly interesting is just how vast it is. Galaxies themselves are relatively rare compared to the enormous distances between them. If you could map the universe on a gigantic scale, you would see galaxies forming long filaments and clusters, almost like glowing threads. Between these threads lie enormous regions where very little exists. It would look a bit like soap bubbles or foam. Thin walls of galaxies surround enormous empty bubbles of space. Inside those bubbles, the darkness can stretch for tens or even hundreds of millions of light years. To imagine that, picture a bubble so large that light, traveling faster than anything else in the universe, would need millions of years just to cross it. Those regions contain almost no galaxies, almost no stars, and only the faint background glow of the universe. They are some of the quietest and coldest places known. And yet, even here, tiny traces of matter still drift through the darkness. A few stray atoms, a faint sprinkle of particles left over from ancient cosmic events. Occasionally a wandering object, like a rogue planet or a lonely comet, might pass through these enormous empty spaces, but such encounters are extremely rare. Most of the time, intergalactic space remains silent and still, a vast frozen ocean between distant islands of light. But even in this quiet cold, the universe still holds surprises, because somewhere within a distant nebula, astronomers discovered something remarkable. A place where gas expanded so rapidly that it cooled below the background temperature of the universe itself, colder than the natural temperature of empty space, colder than almost anything known in nature. A strange object with a fitting name, the Boomerang Nebula. When we talk about the coldness of space, the number that usually comes up is about 2.7 Kelvin, that is, the gentle background temperature of the universe, the quiet warmth left behind by the ancient glow of the early cosmos. For a long time, scientists assumed that nothing in nature could become colder than that. After all, if the universe itself sits at that temperature, how could anything drop below it? It would be like trying to cool something below the temperature of the room it sits in. But the universe often surprises us. Somewhere about 5,000 light years from Earth, inside our own Milky Way galaxy, astronomers found a strange cloud of gas that broke this expectation completely. This object is known as the Boomerang Nebula, and for a time, it held the record as the coldest natural place ever discovered in the universe. To understand how unusual this is, Let's first imagine what a nebula is. A nebula is a giant cloud of gas and dust floating through space. Some nebulae glow brightly because stars inside them light up the surrounding gas. Others appear as dark shapes because thick dust blocks the light behind them. Many nebulae are enormous. Some stretch across dozens of light years, which means light would take dozens of years just to cross them. If one of those clouds replaced our solar system, it could easily swallow the entire region from the Sun, all the way past Pluto, many trillions of times over. The Boomerang Nebula, however, is not famous for its size. It is famous for its temperature. Measurements show that parts of this nebula reach about 1 Kelvin. That is only 1 degree above absolute zero. To picture how cold that is, imagine the coldest place on Earth. The lowest temperature ever recorded on our planet happened in Antarctica, where thermometers once measured about -89 degrees Celsius during a brutal winter storm that is already cold enough to freeze exposed skin quickly. But the Boomerang Nebula is far colder. Its temperature sits near -272 degrees Celsius, which is more than 3 times colder than Antarctica's record cold. It is also colder than the natural background temperature of space itself. And that's what makes it so remarkable, because normally, the faint glow of the universe gently warms everything to around 2.7 Kelvin. But inside the Boomerang Nebula, something strange is happening. The gas there is cooling itself so efficiently that it drops below that cosmic background temperature. It is as if a small pocket of the universe has created its own deeper freezer. When astronomers first realized this, they were amazed, because nature does not usually create conditions this cold without special circumstances. So what exactly is the Boomerang Nebula? Interestingly, it is connected to the life cycle of a dying star. Many people imagine stars simply burning until they suddenly explode or fade away. But the process is often more gradual. When a star similar to our Sun begins reaching the end of its life, it starts shedding its outer layers of gas into space. These layers drift outward slowly at first, forming expanding clouds around the aging star. Over time, those clouds grow larger and larger. Eventually, they become what astronomers call a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. Early astronomers gave them that name because they looked like small round disks in early telescopes. The Boomerang Nebula is one of these expanding clouds. At its center sits an aging star that has begun throwing off huge amounts of gas. But what makes this particular nebula unusual is how fast that gas is expanding. The material is rushing outward at incredible speed, and when gas expands rapidly, something interesting happens. It cools. You may have experienced a small version of this without realizing it. If you spray compressed air from a can, the metal nozzle becomes cold very quickly. The gas inside the can expands suddenly as it leaves, and that rapid expansion causes the temperature to drop. The Boomerang Nebula is doing something similar, but on a cosmic scale. The gas pouring away from its central star expands so quickly that it cools dramatically. Faster expansion means stronger cooling, and in this case, the cooling becomes powerful enough to overcome even the faint warmth of the cosmic microwave background. The result is a region of space colder than the universe around it. If you could somehow place a thermometer inside the Boomerang Nebula, it would measure temperatures even lower than the natural temperature of empty space. That might sound almost impossible, yet nature has quietly built this extreme refrigerator far from Earth. The nebula also gets its name from its unusual shape. Images taken by powerful telescopes show that its expanding gas forms 2 large, curved lobes. When seen from certain angles, these curved structures resemble the shape of a boomerang thrown through the air. But the shape is only part of the story. The real wonder lies in the physics happening inside that cloud. A quiet, expanding wind of gas, slowly cooling itself to temperatures just above absolute zero. And the Boomerang Nebula is not the only place where deep cosmic cold appears. Across the universe, There are wandering planets, frozen clouds, and distant objects drifting far from the warmth of stars. Some of them experience temperatures that rival the coldest places we can imagine, including lonely planets that wander through space without any star to keep them warm. The Boomerang Nebula holds a strange record in the universe. It is colder than the natural background temperature of space. At first, that might sound impossible. After all, space itself sits at about 2.7 Kelvin, which is already incredibly cold. That is, about minus 270 degrees Celsius, far colder than the harshest winter anywhere on Earth. So how could a cloud of gas drop even lower than that? The answer lies in something that happens when gas expands very quickly. To understand this, imagine holding a can of compressed air. If you press the nozzle and spray the gas out, something interesting happens almost immediately. The metal tip of the can becomes cold. Sometimes it even feels icy to the touch. Why does that happen? Inside the can, the gas is packed tightly together under pressure. The particles are squeezed close to one another, constantly colliding. But the moment the gas escapes into the open air, it spreads out rapidly. The particles move away from each other, and as they do, they lose energy. That loss of energy causes the temperature to drop. You may have noticed something similar if you've ever used a bicycle pump. When you compress air inside the pump, it becomes warm. But when air expands quickly, the opposite happens. It cools. The Boomerang Nebula is doing this exact process, but on a scale that is almost impossible to imagine. At the center of the nebula sits an aging star. Long ago, this star was probably similar to our Sun. It burned hydrogen for billions of years, shining steadily and warming the surrounding space. But stars do not stay the same forever. As they run low on fuel, their outer layers begin to swell and loosen. Eventually, the star starts releasing those outer layers into space. Gas begins flowing outward from the star in enormous waves. In the Boomerang Nebula, this gas is expanding extremely fast. The material rushes outward at speeds of about 160 kilometers per second. That's roughly 576,000 kilometers per hour. To picture that speed, imagine a commercial airplane traveling around 900 kilometers per hour. The gas in the nebula is moving more than 600 times faster than that plane. Another way to imagine it is this. If something moved that fast on Earth, it could travel from Manila to Tokyo in less than 1 minute. That's how quickly the gas is spreading outward. As this gas expands, it becomes thinner and thinner. The particles drift farther apart, and just like the air leaving the compressed can, the temperature drops. But here's the surprising part. Because the gas expands so rapidly, it cools faster than the faint background radiation of the universe can warm it. Normally, the cosmic microwave background keeps everything at around 2.7 Kelvin. But inside the Boomerang Nebula, the cooling happens so strongly that the gas falls below that temperature. Measurements suggest that parts of the nebula reach about 1 Kelvin. That is only 1 degree above absolute zero, the theoretical coldest temperature possible. To help picture that, imagine the temperature scale as a staircase. At the top are warm environments like Earth's surface. Then come colder places, like Antarctica. Far below that sits the background temperature of space. But the Boomerang Nebula has stepped down one more stair. It sits in a deeper level of cold. It's a bit like having a freezer inside a freezer. But how did astronomers figure this out? They could not simply fly a thermometer into the nebula. Instead, they studied the light coming from the gas. Atoms and molecules emit very specific signals when they move and vibrate. By observing these signals with radio telescopes, scientists can estimate how much energy the gas particles have. Less energy means slower motion, and slower motion means lower temperature. When astronomers measured the signals coming from the Boomerang Nebula, they discovered something remarkable. The particles were moving incredibly slowly, so slowly that the temperature had to be below the cosmic background temperature. This discovery showed just how strange and creative nature can be. Even in a universe that is already freezing cold, certain conditions can push temperatures even lower. But the Boomerang Nebula will not stay this cold forever. As the gas continues spreading outward, it will gradually mix with the surrounding environment. Eventually, the faint warmth of the cosmic microwave background will slowly bring its temperature back up toward that universal baseline. In other words, this deep freeze is temporary, a brief moment in the life of a dying star. Still, it reminds us of something fascinating. Cold in the universe is not just one simple number. Different places can experience very different temperatures depending on their surroundings. Some regions are warmed by nearby stars, others are cooled by expanding gas, and some objects drift through space completely alone, far from any source of warmth. Among the most mysterious of these lonely travelers are rogue planets, worlds that wander through the galaxy without a star. Planets that drift through the darkness, endlessly moving through some of the coldest environments the universe can create. Most of the planets we know live close to a star. Earth circles the Sun once every year. Mars, Jupiter, and the other planets in our solar system follow their own steady paths around that same warm center. Stars act like cosmic campfires. They give off enormous amounts of energy, and the planets nearby receive some of that warmth. Even very distant planets in our solar system still feel the sun's influence. Pluto, for example, sits about 6 billion kilometers from the sun at its farthest point. That distance is so large that sunlight there is extremely weak. To picture it, imagine standing under a bright street lamp at night. Now walk about 150 meters away from that lamp. The light becomes faint and dim. That is similar to how weak sunlight feels on Pluto compared to Earth. And yet, Pluto still receives some warmth from the sun. But not all planets are lucky enough to have a star. Some planets wander through space completely alone. Astronomers call these worlds rogue planets. They are sometimes described as orphan planets because they have no parent star to orbit. Instead, they drift silently through the darkness of the galaxy. How do planets end up like this? Most scientists believe many rogue planets once belonged to normal solar systems. During the chaotic early stages of planetary formation, young planets can move around in unstable orbits. Large planets, especially massive ones like Jupiter, can disturb the paths of smaller planets nearby. Sometimes gravity acts like a powerful slingshot. A close encounter between two planets can fling one of them outward at tremendous speed. Once a planet is thrown far enough away from its star, it may never return. It escapes into the galaxy. Imagine a group of children playing on a spinning playground merry-go-round. If one child loses their grip and is thrown outward, they fly away from the center and land far away. Something similar can happen in young planetary systems. The result is a planet traveling through space. Without any star nearby, astronomers believe there could be billions of rogue planets in our Milky Way galaxy alone. Some estimates even suggest they may be as common as stars. That means for every glowing sun in the sky, there could be a lonely planet wandering through the dark. So what would the temperature be on such a world? Without a nearby star, there is almost no incoming energy, no sunlight, no warm seasons, no gentle daylight heating the surface. Instead, the planet slowly loses its heat into space. Over millions or billions of years, the surface becomes incredibly cold. Eventually, temperatures may drop close to the background temperature of the universe, around 2.7 Kelvin, or about minus 270 degrees Celsius. To imagine that kind of cold, picture a large metal object left outside on a winter night. By morning, it feels icy to the touch because it has released heat into the cold air. Now imagine that object left alone, not for one night, but for millions of years, in a place far colder than any winter. That is the slow cooling process rogue planets experience. Their surfaces can freeze solid, Any oceans that once existed would turn into thick layers of ice. Atmospheres may collapse and freeze onto the surface. In some cases, gases like nitrogen or carbon dioxide could form icy frost covering the ground. The landscape would be dark and silent. No sunrise, no sunset, just endless night. But here's something interesting. Even rogue planets may not be completely frozen inside. Deep beneath the surface, heat from the planet's core can remain for a very long time. This heat comes from two main sources. One source is leftover warmth from when the planet first formed. Another comes from radioactive elements slowly breaking down inside the planet's rocks. This process releases small amounts of energy over long periods. It's similar to how a baked potato stays warm for a while after leaving the oven. The outside cools quickly, but the inside remains warm much longer. For large rogue planets, that internal warmth could last billions of years. In fact, some scientists have wondered if deep underground oceans might still exist beneath thick layers of ice on certain rogue planets. Imagine a frozen world drifting through interstellar space, its surface colder than almost anywhere imaginable. But miles below the ice, hidden oceans of liquid water, quietly moving in the darkness. It's a strange thought. A lonely world with a frozen shell and a warm heart deep inside. Still, from the outside, these planets are among the coldest objects in the galaxy. They wander silently between the stars, moving through regions where temperatures hover just above absolute zero. And rogue planets are not the only frozen worlds we know. Even within our own solar system, far from the sun's warmth, there are places where temperatures fall to astonishing lows. Icy moons, distant dwarf planets, ancient objects that have remained frozen since the early days of the solar system. Some of them experience temperatures colder than -220 degrees Celsius, making them some of the coldest surfaces we have ever explored. When we think about cold places in space, it's easy to imagine distant galaxies or lonely rogue planets drifting through the dark, but some of the coldest environments we know actually exist much closer to home. They are located in the far outer regions of our own solar system. Out there, sunlight becomes incredibly weak. The warmth from the sun fades slowly as distance increases. By the time you travel billions of kilometers away, the sun no longer feels like a bright source of heat. Instead, it looks more like an extremely bright star, shining in the distance. One of the most famous examples is Pluto. For many years, Pluto was considered the 9th planet of our solar system. Today it is classified as a dwarf planet, but it remains one of the most fascinating icy worlds we know. Pluto travels around the Sun at an average distance of about 5.9 billion kilometers. To picture that distance, imagine driving a car non-stop at highway speed, about 100 kilometers per hour. Even without stopping to sleep or eat, it would take more than 6,700 years to drive that far. At such an enormous distance, sunlight becomes very faint. If you stood on Pluto during the daytime, the sun would appear much smaller in the sky than it does from Earth. It would shine only about 1,000th as brightly as it does here. That means the warmth reaching Pluto is extremely limited. As a result, surface temperatures there can drop to around -230 degrees Celsius. That's colder than any natural temperature recorded on Earth by more than 140 degrees. To imagine how cold that is, think about placing a piece of metal into a deep freezer set to its coldest setting. After several hours, the metal becomes painfully cold to touch. Now imagine a freezer far colder than anything in your kitchen, colder than industrial freezing equipment, and leaving that metal there for years. That begins to hint at the temperatures on Pluto. The landscape itself is made mostly of ice, but not just the kind of ice we are familiar with. On Pluto, many different substances freeze solid. Water becomes rock hard, like stone. Nitrogen forms vast frozen plains. Methane and carbon monoxide freeze into crystals across the surface. Some of these icy plains stretch for hundreds of kilometers. One famous region, known as Sputnik Planitia, is a giant basin filled with nitrogen ice. It is roughly 1,000 kilometers across, which is about the distance from Manila to Hong Kong. Yet Pluto is not the only frozen world in the outer solar system. Another remarkable example is Triton, a moon that orbits the giant planet Neptune. Triton sits even farther from the Sun than Pluto. Because of this, its surface temperature can fall to about -235 degrees Celsius. That makes Triton one of the coldest solid surfaces ever measured in our solar system. Triton is especially interesting because it has a very thin atmosphere, made mostly of nitrogen gas. At such low temperatures, this atmosphere behaves in unusual ways. During certain seasons, nitrogen gas can freeze and fall to the surface like snow. Imagine standing in a place where snowflakes are not made of water, but of frozen nitrogen gas. The ground beneath your feet would be covered in pale frost, glimmering faintly in the weak sunlight. Even more surprising, Triton has been observed producing ice geysers. These geysers shoot dark plumes of material several kilometers into the air. To picture that height, imagine a fountain spraying upward, nearly 3 times taller than the Burj Khalifa, the tallest building on Earth. But instead of hot water like geysers on Earth, Triton's plumes contain nitrogen gas and dark dust escaping from beneath the frozen surface. Other distant objects in our solar system are even colder. Many of them are small icy bodies orbiting far beyond Neptune. Some are only a few hundred kilometers wide, roughly the size of large cities. Yet despite their small size, they have remained frozen for billions of years. These worlds formed during the earliest days of the solar system and have changed very little since then. In many ways, they are like cosmic time capsules. If you could walk across one of these distant icy objects, the ground might feel as hard as stone. Even though it is made of frozen gases, your footsteps would leave marks in frost that has remained undisturbed since before Earth even formed. The sky above would appear almost completely black, even during the day. The sun would shine faintly, like a bright star, and the temperature would remain hundreds of degrees below freezing. These frozen worlds remind us of something remarkable. Even within the boundaries of our own solar system, temperatures can reach levels that feel almost impossible to imagine. Yet beyond these distant icy planets lies an even larger region, a vast ring of ancient objects circling the outer edges of our solar system. A place where the sunlight grows weaker still, quiet frozen region known as the Kuiper Belt. Beyond the orbit of Neptune, the outermost major planet of our solar system, space begins to change. The familiar region of planets slowly fades away. Instead of large worlds like Jupiter or Saturn, the landscape becomes filled with countless smaller icy objects drifting through the dark. This distant region is called the Kuiper Belt. You can think of it as a vast ring of ancient debris left over from the birth of our solar system billions of years ago, when the sun and planets were still forming. Huge clouds of gas and dust swirled around the young star. Some of that material gathered together to form planets, but not all of it. Many smaller pieces remained scattered across the outer edges of the solar system. Over time, these fragments settled into a wide belt, orbiting far beyond Neptune. Today, astronomers estimate that the Kuiper Belt may contain hundreds of thousands of icy objects larger than 100 kilometers across, along with millions of smaller ones. To picture that size, imagine a single object about 100 kilometers wide. That's roughly the distance between Manila and Batangas City. Now imagine hundreds of thousands of frozen worlds that size drifting in the dark. Some of them are even larger. Pluto itself is one of the biggest members of the Kuiper Belt, measuring about 2,377 kilometers across, which is roughly the distance from Manila to Taipei and back again. Despite the huge number of objects there, the Kuiper Belt is still incredibly empty. The objects are spread across a region so large that the distance between them can be millions of kilometers. If you were standing on one of these icy bodies and looking out across the Kuiper Belt, you would not see a crowded field of rocks. Most of the time, the sky would look almost completely empty. Another frozen object might be so far away that even a powerful telescope would struggle to spot it. But what really makes the Kuiper Belt remarkable is the temperature. At these extreme distances from the Sun, sunlight becomes incredibly weak. Neptune orbits about 4.5 billion kilometers from the Sun. The Kuiper Belt begins just beyond that and stretches much farther outward. By the time sunlight reaches these distant objects, it has spread across such a large area that only a tiny fraction of its original warmth remains. Imagine a flashlight shining brightly in a dark room. Up close, the beam is strong and bright, but if you walk far enough away, the light becomes faint and barely noticeable. Sunlight behaves the same way across space. At the distance of the Kuiper Belt, the Sun shines hundreds of times weaker than it does on Earth. Because of this, temperatures in the Kuiper Belt often drop below -220 degrees Celsius. That's cold enough for many gases to freeze solid. On Earth, substances like methane or nitrogen usually exist as gases in the air, but in the Kuiper Belt, these substances can form frost and ice covering the surfaces of distant objects. Imagine a landscape where even the air we breathe on Earth would freeze instantly into crystals. That is the kind of environment these distant worlds experience. The surfaces of Kuiper Belt objects are often coated with layers of frozen methane, ammonia, and water ice. Over billions of years, cosmic radiation slowly darkens these icy surfaces, giving many of them a reddish color. Some objects look like dark red snowballs drifting through the cold. And the cold here is not temporary. Unlike Earth, where seasons change and temperatures rise and fall, many Kuiper Belt objects remain frozen at nearly the same temperature for millions of years. Sunlight is too weak to warm them much, and their internal heat has long since faded. These worlds are like ancient relics from the early solar system, preserved in deep freeze. You might wonder something interesting. If the Kuiper Belt is so cold and distant, why didn't its objects gather together to form another planet? After all, the inner solar system formed several large planets. The answer comes down to gravity and distance. Far from the Sun, objects move more slowly in their orbits. Collisions between icy bodies happen less often, and when they do collide, the impacts are sometimes too gentle to allow them to merge together easily. Instead of forming one large planet, the material remained scattered. Over billions of years, the Kuiper Belt became a quiet graveyard of icy leftovers from planetary formation. Occasionally, one of these objects gets nudged inward by gravitational interactions. When that happens, it may become a comet, traveling towards the inner solar system with a glowing tail. But most Kuiper Belt objects remain far away, locked in their slow, cold orbits. Still, even this distant region is not the true edge of the solar system. Far beyond the Kuiper Belt lies an even larger and more mysterious structure, a distant spherical cloud of icy bodies surrounding our entire solar system, a place so far away that sunlight becomes almost meaningless. A frozen shell known as the Oort Cloud. If the Kuiper Belt marks the distant outskirts of the solar system, then the Oort Cloud represents something even more remote. It is believed to be the farthest region still connected to our Sun, and it is unimaginably far away. To understand just how far, let's start with a familiar distance. Earth orbits the Sun at about 150 million kilometers. This distance is often used as a measuring unit in astronomy and is called 1 astronomical unit, or 1 AU. Neptune, the outermost major planet, orbits at about 30 AU from the Sun. That means Neptune is 30 times farther from the Sun than Earth is. The Kuiper Belt begins around that distance and stretches outward to roughly 50 AUT. Already, this region feels extremely distant. But the Oort Cloud lies far beyond even that. Astronomers believe it begins somewhere around 2000 AU from the Sun and may extend outward to 100,000 AU/RU or more. To picture that distance, imagine shrinking the distance from Earth to the Sun down to 1 meter. In that scale model, Neptune would sit about 30 meters away, roughly the length of a small swimming pool. The Kuiper Belt would extend slightly beyond that, but the Oort Cloud would begin about 2 kilometers away and stretch as far as 100 kilometers from the center. That's roughly the distance from central Manila to nearby provinces. And remember, that entire enormous distance would still represent objects gravitationally tied to our Sun. The Oort Cloud is not a flat ring like the Kuiper Belt. Instead, scientists believe it forms a giant spherical shell surrounding the solar system in all directions. If the planets orbit inside a thin disk, the Oort Cloud would be like a massive cloud of icy debris wrapping around that disk like a giant bubble. Inside this distant shell may exist trillions of icy bodies. Most of them are thought to be the frozen leftovers from the early days of planet formation, long ago, when the giant planets like Jupiter and Saturn were still settling into their orbits. Their powerful gravity scattered many smaller objects outward. Some were thrown completely out of the solar system. Others were pushed so far away that they now drift slowly in the distant Oort Cloud. These objects move extremely slowly around the Sun. At such great distances, the Sun's gravity becomes very weak. An object in the outer Oort Cloud might take millions of years to complete a single orbit around the Sun. To imagine that timescale, consider this. Modern humans have existed for roughly 300,000 years. That means a single orbit of a distant Oort Cloud object could take 10 times longer than the entire history of our species. Everything out there moves quietly and slowly, and the temperatures are astonishingly low. Sunlight at those distances becomes almost meaningless. The Sun would appear only slightly brighter than other stars in the sky. Its warmth would be barely noticeable. Without that warmth, objects in the Oort Cloud cool to temperatures very close to the natural background temperature of space, around 2.7 Kelvin, or about minus 270 degrees Celsius. That is only a few degrees above absolute zero. To imagine how cold that is, think about the coldest freezer you can picture. Even powerful industrial freezers used in laboratories rarely drop below minus 80 degrees Celsius. The Oort Cloud is nearly 3 times colder than that. It is so cold that almost all known gases become solid. Water ice, methane ice, ammonia ice, and carbon monoxide ice can all exist there as frozen materials. If you stood on the surface of an Oort Cloud object, the ground beneath your feet might feel like rock, but in reality, much of it would be made from frozen substances that on Earth would normally exist as gases. The sky above would be almost completely black. The Sun would appear as a small bright star, barely larger than the others around it, and the temperature would remain steady for millions of years. Yet even this distant region occasionally interacts with the rest of the solar system. Every so often, a passing star or the gentle pull of gravity from the Milky Way can disturb an object in the Oort Cloud. When that happens, the object may slowly begin falling inward toward the Sun. As it approaches the inner solar system, sunlight warms its frozen surface. Ice begins to vaporize into gas. Dust and gas stream away from the object, forming the glowing tails we recognize as comets. These long-period comets often come from the Oort Cloud. Some of them take tens of thousands of years to return after passing near the Sun. Others may visit the inner solar system only once before drifting away again. So even though the Oort Cloud lies far beyond the planets, it still sends occasional visitors into our cosmic neighborhood. It is the distant frozen edge of the Sun's influence. But the solar system is only a tiny part of the galaxy. Far beyond it lie enormous clouds of gas and dust drifting through interstellar space, and surprisingly, some of the coldest environments where new stars are born exist inside these dark cosmic clouds. Far beyond the frozen edges of our solar system, space becomes filled with something different. Not planets, not comets, but enormous clouds of gas and dust drifting through the galaxy. These clouds are often called molecular clouds, and some of them are among the coldest places where new stars are born. At first, that might sound surprising. Most people imagine stars forming in bright, glowing regions, full of heat and energy. But the truth is almost the opposite. Many stars begin their lives inside very cold, dark clouds. These regions are so dense with gas and dust that they block starlight from passing through. From Earth, they sometimes appear as dark shapes against the glowing background of the Milky Way. It can look as if a piece of the starry sky has simply been erased. But those dark patches are not empty. They are actually filled with enormous amounts of material. To understand their size, imagine a cloud stretching across 100 light years. That means light, traveling faster than anything in the universe, would take 100 years just to cross from one side of the cloud to the other. If we tried to compare that to something on Earth, it would be like a cloud large enough to stretch from Manila all the way across the entire Pacific Ocean and still keep going. These clouds are enormous, yet despite their size, they remain extremely cold. Temperatures inside many molecular clouds can fall to around 10 Kelvin. That is about minus 263 degrees Celsius. While that might be slightly warmer than the background of empty space, it is still unimaginably cold by Earth standards. Remember that Antarctica's record low temperature is around minus 89 degrees Celsius. So molecular clouds are almost 3 times colder than the coldest place ever recorded on our planet. Why are they so cold? The answer has a lot to do with darkness. Inside these clouds, thick dust blocks much of the light coming from nearby stars. Without that starlight, there is very little energy to warm the gas. It's a bit like standing deep inside a cave. Outside, the sunlight might be bright and warm, but deep inside the cave, far from the entrance, the air becomes cool and still. Molecular clouds are like cosmic caves floating through space. The dust shields the interior from radiation, allowing temperatures to drop dramatically. Another reason these clouds remain cold is their density. That might sound strange, because we usually think of dense materials as warm, but in space, dense is still incredibly thin compared to Earth's atmosphere. A molecular cloud might contain only a few thousand particles per cubic centimeter. That may sound like a lot at first. A molecular cloud might contain only a few thousand particles per cubic centimeter. That may sound like a lot at first, but the air around you right now contains about 10 quintillion particles in that same space. To picture that difference, imagine a large sports stadium packed with people. Now imagine removing everyone except for just one person sitting alone in the stands. That is roughly the difference between air on Earth and the gas inside these cosmic clouds. Even though molecular clouds are called dense by space standards, they are still incredibly empty. Because of this, heat moves very slowly inside them. Energy cannot easily spread from one region to another. The result is a calm, cold environment where atoms drift quietly through the darkness. But something fascinating happens inside these clouds. Despite the cold, gravity slowly begins pulling some regions together. Tiny pockets of gas grow slightly denser than the surroundings. As more gas drifts inward, those pockets become heavier. And over long periods of time, gravity keeps pulling more and more material into the same area. It's similar to the way snow gathers during a snowfall. A few flakes land on the ground, then more fall on top of them. Eventually, the pile becomes larger and heavier. Inside molecular clouds, gas gathers in the same slow way. Over thousands or even millions of years, these dense pockets continue growing, and as they grow heavier, gravity squeezes the gas tighter and tighter. Something interesting happens during that squeezing. The temperature begins to rise. The particles start moving faster. Eventually, if enough gas gathers together, the center of the cloud becomes hot and dense enough to ignite nuclear fusion. That moment marks the birth of a new star. So strangely enough, many stars are born inside some of the coldest environments in the galaxy. Cold clouds collapse slowly under gravity until the pressure creates a hot newborn star at the center. You can imagine it like a small spark forming inside a giant frozen cloud. The darkness slowly gives way to light, and the cold birthplace of a star begins to glow. But before that happens, these molecular clouds remain among the coldest natural environments in space, hidden in darkness, drifting quietly through the galaxy. And inside those clouds, the extreme cold allows something unusual to happen with the chemistry of space. Because when temperatures drop low enough, molecules can behave in ways that rarely occur anywhere else in the universe. When temperatures drop to extremely low levels, something unusual begins to happen to matter. Atoms and molecules move more slowly, much more slowly. Earlier we talked about how temperature is really a measure of motion. Warm materials have fast-moving particles. Cold materials have slower ones. But in the deep cold of space, that motion slows down to an almost peaceful crawl. Inside many molecular clouds, where temperatures hover around 10 Kelvin, atoms drift so slowly that they barely bump into each other. To picture this, imagine a busy city street at midday. Cars are moving quickly. People cross the road. Bicycles pass by. Everything feels energetic and crowded. Now imagine that same street at 3 o'clock in the morning. The traffic disappears. A single car might pass every few minutes. The quiet becomes noticeable. That slow, quiet motion is a bit like the behavior of atoms inside extremely cold regions of space. And this calm environment allows chemistry to happen in ways that are difficult to recreate anywhere else. On Earth, many chemical reactions happen quickly because atoms are constantly colliding. Heat provides energy that helps break bonds between atoms so new ones can form. But in ultra-cold space, atoms move slowly and gently. Instead of violent collisions, they sometimes meet softly and stick together. This leads to the formation of molecules that might seem surprising. For example, scientists have discovered molecules in space that include water, ammonia, carbon monoxide, methanol, and even more complex organic compounds. Some of these molecules are quite fragile. If they were placed in warmer environments, they would break apart easily. But in the cold darkness of molecular clouds, they can survive. Dust grains floating through the cloud also play an important role. These grains are incredibly tiny. Many are about the size of fine smoke particles, far smaller than the width of a human hair. Yet they act like little platforms where chemistry can take place. Imagine tiny specks drifting through space, each one coated with thin layers of frozen material. Atoms can land on these grains and remain there. Because the temperature is so low, they do not bounce away quickly. Instead, they linger. And when another atom lands nearby, the two may slowly combine. It's a bit like snowflakes settling on the ground during a calm winter night. Each flake lands gently and stays where it falls. Over time, layers build up. On cosmic dust grains, layers of frozen molecules accumulate in a similar way. Water ice can form, so can frozen carbon dioxide, methane, and other substances. These icy coatings can grow thicker and thicker over thousands of years. Eventually, a dust grain drifting through a molecular cloud may carry a tiny collection of frozen molecules on its surface. In a sense, it becomes a miniature chemistry laboratory floating through space. What makes this even more fascinating is the variety of molecules astronomers have discovered. More than 200 different types of molecules have been detected in interstellar space. Some are simple, containing just 2 atoms. Others are more complex, including chains of carbon atoms that resemble the building blocks of organic chemistry. To picture how tiny these molecules are, imagine a single drop of water. That drop contains roughly 1 sextillion molecules, which is a number with 21 zeros after it. Now imagine detecting just a few of those molecules floating in a cloud that stretches across dozens of light years. That is the kind of challenge astronomers face when studying interstellar chemistry. They cannot scoop up samples directly. Instead, they observe the faint signals that molecules emit when they rotate or vibrate. Each type of molecule produces a unique pattern of radiation, almost like a fingerprint. By studying those patterns with radio telescopes, scientists can identify which molecules exist inside distant clouds. Through these observations, astronomers have learned that cold molecular clouds are rich with frozen chemistry, and the extreme cold plays a crucial role. If the clouds were warmer, many of these molecules would break apart or evaporate. The low temperature allows them to survive long enough to accumulate. You might wonder why this matters. After all, these molecules are drifting through empty space, far from planets or living creatures. But the answer connects to something very important. These cold molecular clouds are the same places where new stars and planetary systems begin to form. When gravity eventually collapses a cloud into a newborn star, some of the surrounding material forms a disk around that star. Inside that disk, planets may begin to grow, and the molecules created during the cold phase of the cloud can become part of those forming planets. In other words, some of the chemistry that happens in the cold darkness of space may eventually become part of worlds like Earth. Tiny frozen molecules drifting through space today might one day become part of oceans, atmospheres, or even living things on distant planets, all because the universe created a calm, cold environment where unusual chemistry could quietly unfold. And those same cold clouds contain something even more familiar: vast amounts of frozen water and other cosmic ices drifting through deep space. When we think about ice, most of us imagine something simple: frozen water, ice cubes in a glass, snow falling gently in winter, or frozen lakes that people skate on during cold seasons. On Earth, ice is something familiar and easy to understand. It forms when water cools below 0 degrees Celsius, turning from liquid into solid crystals. But in the deep cold of space, ice can mean something much broader. Out there, many different substances can freeze. Water freezes, of course, but so do gases that we normally never see as solids on Earth. Methane can freeze, carbon dioxide can freeze, ammonia can freeze. Even carbon monoxide, a gas that is invisible and deadly on Earth, can become solid ice in space. This means that many regions of the universe are filled with what scientists call cosmic ice. These frozen materials often coat tiny dust grains drifting through molecular clouds. Earlier we talked about how small those grains are. Many are smaller than smoke particles floating in the air. Yet, over long periods of time, they slowly gather layers of frozen molecules. Imagine a grain of dust floating through a cold cloud. Atoms and molecules drifting nearby gently land on its surface. Because the temperature is so low, the molecules do not bounce away again. Instead, they stick. Another molecule arrives, then another. Over thousands or even millions of years, a thin, icy coating builds up. It's a bit like frost forming on a window during a cold winter night. The frost begins as tiny crystals. Slowly it spreads and thickens as more water vapor freezes onto the glass. In molecular clouds, similar frost layers form on dust grains, but instead of just water ice, the layers can contain a mixture of many frozen chemicals. Astronomers have detected cosmic ice made of water, methane, ammonia, carbon dioxide, methanol, and other molecules. These frozen layers can sometimes grow thick enough to completely cover the dust grain beneath, and these icy particles are everywhere inside certain molecular clouds. To picture how widespread they are, imagine a cloud stretching across 50 light years. That means light would take 50 years just to cross it. Inside that enormous region, trillions upon trillions of tiny icy grains drift quietly in the darkness, each one carrying microscopic layers of frozen chemistry. But how do scientists know these ices exist? After all, they cannot travel to those clouds and collect samples. Instead, they use telescopes that detect infrared light. Different molecules absorb and emit light in specific patterns. When starlight passes through a cloud filled with cosmic ice, certain wavelengths of that light are absorbed. By studying those patterns, astronomers can identify the frozen substances hidden within the cloud. It's a bit like shining a flashlight through colored glass. If the glass absorbs red light but lets blue light pass through, the beam on the other side will look different. In the same way, frozen molecules in space leave recognizable fingerprints in the light passing through them. Using this method, scientists have confirmed that cosmic ice is extremely common. In fact, water ice may be one of the most widespread solid materials in the universe. You might wonder something interesting. If water ice is so common in space, where did it come from? The answer goes back to the early stages of star formation. Inside cold molecular clouds, oxygen atoms and hydrogen atoms drift slowly through space. When they meet on the surface of a dust grain, they can combine. 2 hydrogen atoms and 1 oxygen atom form a water molecule. Once the water molecule forms, the low temperature keeps it frozen in place. Over time, layer after layer of water ice builds up. This process can create icy coatings that later become part of new planetary systems. In fact, much of the water in our own solar system may have formed this way long before Earth even existed. Some of the ice inside comets likely originated in ancient molecular clouds billions of years ago. When comets later collided with young planets, they may have delivered some of that water to planetary surfaces. It's possible that part of Earth's oceans began as frozen molecules drifting through deep space. But cosmic ice does more than just store water. It also provides surfaces where chemical reactions can happen. When ultraviolet radiation from nearby stars strikes these icy layers, it can trigger reactions that create more complex molecules. Over time, simple frozen compounds can transform into larger organic molecules. Some scientists believe this process may have helped create ingredients important for life. But even without that possibility, cosmic ice plays a crucial role in the universe. It stores molecules, it protects fragile compounds from radiation, and it travels through space as part of dust grains that eventually become part of forming stars and planets. All of this happens in the deep cold of molecular clouds, places where temperatures remain only a few degrees above absolute zero. And in those same cold environments, gravity slowly gathers material together. Eventually, those frozen clouds begin collapsing inward. And from some of the coldest places in the universe, something bright and powerful is born. A new star. It may seem strange at first, but many stars begin their lives in some of the coldest environments in the universe. When people imagine the birth of a star, they often picture fire and heat from the very beginning. Bright light, burning energy, explosions of heat and power. But the earliest stage of star formation is actually quiet and cold. Stars are born inside the same dark molecular clouds we explored earlier. These clouds drift slowly through galaxies, made mostly of hydrogen gas mixed with dust and frozen molecules. And inside them, the temperature remains incredibly low. Many star-forming clouds sit around 10 Kelvin, which is about minus 263 degrees Celsius. To imagine that cold, think again about the coldest natural temperatures on Earth. Even the harshest Antarctic winter, reaching about minus 89 degrees Celsius, is still far warmer. The gas inside these clouds is almost 3 times colder than the coldest temperature ever recorded on our planet. So why does star formation begin in such cold places? The answer has a lot to do with gravity and motion. Remember how temperature reflects how fast particles move. When gas is warm, Its particles move quickly in all directions. That motion creates pressure pushing outward. Imagine shaking a jar filled with small marbles. The marbles bounce around, hitting the walls and each other constantly. Their movement keeps them spread out. Warm gas behaves in a similar way. Fast-moving particles push against gravity, resisting collapse. But when gas becomes very cold, the particles move slowly. Much more slowly. The outward pressure weakens. Now gravity has an easier time pulling the gas together. You can picture it like a group of people standing on a frozen lake. If everyone runs in different directions quickly, the group spreads out. But if everyone moves slowly and gently, gravity-like forces could draw them closer together. Inside cold molecular clouds, something similar happens. Tiny regions become slightly denser than their surroundings. Perhaps a nearby supernova shockwave passes through the cloud, or two parts of the cloud collide gently. Or gravity simply gathers gas, little by little, over time. Once a region becomes dense enough, gravity begins pulling material inward. More gas drifts toward the center. The growing clump becomes heavier, and as it grows heavier, gravity pulls even more gas toward it. This process can continue for thousands or even millions of years. The cloud slowly collapses inward, under its own weight. During the early stages, everything remains cold. The gas falls inward quietly, but as more material gathers at the center, something begins to change. The pressure increases, gas particles become squeezed closer together, and when particles are squeezed tightly, they begin to move faster again. The temperature slowly rises. It's similar to what happens when you pump air into a bicycle tire. The pump becomes warm in your hand because the air inside is being compressed. Inside a collapsing cloud, the same idea applies. Gravity squeezes the gas tighter and tighter. The center grows warmer and denser. Eventually, a glowing object forms in the middle of the cloud. This is called a protostar. A protostar is not yet a true star. It does not produce energy through nuclear fusion yet, but it is the beginning of that process. Gas continues falling inward. Pressure and temperature continue rising. At the center of the protostar, temperatures climb to millions of degrees. To picture that, imagine the surface of the sun, which is about 5,500 degrees Celsius. Now imagine temperatures more than 1,000 times hotter than that. When the core reaches around 10 million degrees, something remarkable happens. Hydrogen atoms begin fusing together to form helium. This process releases enormous amounts of energy. The protostar suddenly becomes a true star. Light and heat begin pouring outward. Radiation pushes against the surrounding gas, and the star begins shining across the darkness of space. What started as a quiet pocket of cold gas becomes a powerful source of energy, a new sun. But the story does not end there. Around the newborn star, leftover gas and dust often form a rotating disk. Inside this disk, small particles collide and stick together. Over time, they grow into larger objects. Pebbles become rocks. Rocks become planet-sized bodies. Eventually, entire planetary systems may form, all beginning inside one of the coldest places in the galaxy. It's a fascinating contrast. The birthplaces of stars are cold, dark, and quiet. Yet from those cold clouds emerge objects that can shine for billions of years. Stars that warm planets, stars that light up galaxies, and stars that make life possible on worlds like our own. But the cold regions of the universe are not limited to star-forming clouds. There are even larger places where matter is extremely rare, enormous stretches of space where galaxies themselves become scarce, vast regions of cosmic emptiness, where the cold darkness spreads for unimaginable distances. If you could step far enough away from galaxies, you would eventually arrive at one of the quietest places in the universe, a region where stars are extremely rare, where matter becomes incredibly thin, where darkness stretches almost endlessly in every direction. These regions are called cosmic voids, and they are some of the largest structures in the universe. To understand what a cosmic void is, it helps to imagine the large-scale shape of the universe. When astronomers map the positions of millions of galaxies, an interesting pattern appears. Galaxies are not spread evenly across space. Instead, they gather along enormous filaments and clusters, forming something that looks a bit like a giant web. Picture the foam on top of a cappuccino. The bubbles create thin walls and edges, leaving empty spaces between them. The universe has a similar structure. Galaxies line the edges of enormous bubbles, and inside those bubbles lie vast empty regions. Those empty regions are cosmic voids. Some voids are unimaginably large. A typical void may stretch tens of millions of light years across. That means light, traveling at its incredible speed of 300,000 kilometers per second, would still need tens of millions of years just to cross from one side to the other. To put that into perspective, imagine shrinking the Milky Way galaxy to the size of a grain of rice. In that scale model, some cosmic voids would still be as large as an entire city. The emptiness is that vast. Inside these regions, galaxies are extremely rare. Sometimes a void that spans 100 million light years might contain only a handful of small galaxies scattered within it. Much of the space inside a void contains almost nothing at all, just a few drifting atoms here and there, tiny traces of gas, and the faint glow of the cosmic microwave background filling the darkness. Because these voids contain so little matter, they are among the coldest environments in the universe. There are very few stars nearby to provide warmth, very little gas to trap energy. Most objects inside a cosmic void slowly cool until they reach the natural background temperature of the universe, around 2.7 Kelvin, or roughly minus 270 degrees Celsius. That temperature may sound familiar now. It is the quiet baseline set by the ancient radiation left over from the early universe. But the feeling of emptiness inside a cosmic void is something that can be difficult to imagine. Even interstellar space inside galaxies contains clouds of gas, dust, and scattered stars. Inside a void, these things become incredibly sparse. Imagine standing in a large empty field at night. The sky stretches above you, filled with distant stars. Now imagine removing almost all of those stars. One by one they fade away. Soon only a few faint points remain in the darkness that begins to hint at the emptiness inside a cosmic void. You might wonder how such enormous empty regions formed. Why would the universe create places with so little matter? The answer goes back to the early stages of cosmic evolution. After the Big Bang, matter in the universe was not perfectly evenly distributed. There were tiny variations in density. Some regions contained slightly more matter than others. Gravity slowly amplified those differences. Regions with slightly more matter began attracting even more material. Galaxies and clusters gradually formed along those denser areas. Meanwhile, regions with slightly less matter lost material over time. Gravity pulled matter away from them toward the growing clusters. Those regions became emptier and emptier. Over billions of years, they expanded into the enormous voids we see today. It's a bit like watching raindrops gather on a window. As droplets merge together, they form thicker streams. Between those streams, the glass becomes clearer and emptier. In the universe, gravity gathered matter into cosmic filaments and clusters. The remaining regions became the vast voids. And because these voids contain so little material, they remain extremely cold and dark. Light from distant galaxies still passes through them. But inside the voids themselves, there are few sources of energy. Only the faint cosmic background radiation continues to glow softly across the darkness. Yet even among these enormous empty regions, some voids stand out for their incredible size. One in particular is so large that astronomers were once stunned when they first discovered it. a vast region of space where galaxies seem almost completely absent, a place known as the Boötes void, a cosmic emptiness so enormous that it challenges our sense of scale in the universe. Among the many empty regions scattered across the universe, one stands out for its incredible size. It is known as the Boötes void, and when astronomers first realized how large it was, many of them were genuinely surprised. To understand why, imagine looking at a map of the universe where galaxies appear as tiny glowing points. Usually, these galaxies gather together in clusters and long threads that stretch across space. Between those threads lie the cosmic voids we talked about earlier. But the Boötes void is not just another typical void. It is enormous. The region stretches about 330 million light-years across. That number is so large that it can be hard to imagine. Light, which travels faster than anything else in the universe, would still need 330 million years just to cross from one side of this void to the other. To help picture that distance, think about the Milky Way galaxy. Our galaxy is about 100,000 light-years wide. Now imagine lining up more than 3,000 Milky Way galaxies side by side. That enormous chain would still be shorter than the width of the Boötes void. It is one of the largest known empty regions in the observable universe. Astronomers first identified this void in the early 1980s while mapping the positions of distant galaxies. As they studied the data, they noticed something unusual. In one part of the sky, galaxies seemed to be missing, where they expected to see hundreds or even thousands of galaxies. There were almost none. At first, researchers wondered if their instruments were malfunctioning, but further observations confirmed the discovery. A huge region of space really was almost empty. Inside the Boötes void, only about 60 galaxies have been found. That may sound like a lot at first, but remember how large the region is. If those 60 galaxies were spread across a volume hundreds of millions of light-years wide, they would be incredibly far apart. It would be like placing a handful of grains of rice across an entire football stadium. Most of the stadium floor would remain empty, and that's similar to the emptiness inside the Boötes void. If you could travel through that region in a spaceship, you might spend millions of years drifting through darkness without ever encountering a galaxy. Stars would appear extremely sparse. Most directions would show nothing but distant pinpoints of light, far beyond the edges of the void. The temperature inside this vast emptiness would remain close to the natural background temperature of the universe, about 2.7 Kelvin, or roughly minus 270 degrees Celsius. Without nearby stars or galaxies, there is very little energy to warm anything. Objects drifting inside the void would slowly cool until they reached that same deep cosmic temperature. The Boötes void also reminds us of something fascinating about the structure of the universe. On the largest scales, the universe resembles a kind of cosmic sponge or foam. Galaxies gather along thin walls and filaments, forming a web-like structure. Between those structures lie the voids, huge bubbles of space where very little matter exists. If you could zoom out far enough to see hundreds of millions of light years at once, the pattern would become clear. Bright threads of galaxies would outline the edges. Dark, empty spaces would fill the gaps between them. It's a bit like looking at soap bubbles floating together. The thin walls between bubbles touch and form a network. Inside each bubble lies mostly empty space. The Boötes void is one of those enormous bubbles, but its size makes it particularly striking. Even astronomers who study the largest structures in the universe find it impressive. You might wonder something interesting. How did such a huge, empty region form? The answer is connected to the same process that created all cosmic voids. Small variations in matter density existed in the early universe. Regions with slightly more matter gradually attracted more material through gravity. Meanwhile, regions with slightly less matter lost material over time. Gravity pulled matter away from them toward the growing clusters and filaments. Over billions of years, those regions became emptier and larger, In some cases, like the Boötes void, the emptiness grew to astonishing scales. Matter continued flowing outward toward surrounding structures, leaving behind a giant bubble of space with very few galaxies. Yet even inside such emptiness, the universe still carries subtle patterns. Astronomers have discovered something curious when studying the ancient radiation left over from the Big Bang. In one direction of the sky, the cosmic background radiation appears slightly colder than expected, a mysterious patch known simply as the cold spot, and some scientists have wondered whether enormous voids, like those scattered across the universe, might help explain why that region appears colder than the rest of the sky. In 2004, astronomers studying the ancient glow of the universe noticed something unusual. As we discussed earlier, the cosmic microwave background fills the entire sky with a faint, nearly uniform temperature. Every direction you look, that background radiation measures about 2.7 Kelvin. But when scientists mapped it with very sensitive instruments, they discovered tiny variations. Some areas were just a little warmer, others were slightly cooler. Most of these differences were incredibly small, often only 100,000th of a degree apart. To picture that difference, imagine measuring the temperature of a large swimming pool. Now imagine detecting a temperature change smaller than a single drop of warm water in that entire pool. That is how subtle most variations in the cosmic background radiation are. But one particular region stood out. In the direction of a constellation called Eridanus, astronomers found a patch of sky that appeared noticeably colder than the surrounding areas. This region became known as the cosmic cold spot. The area stretches roughly 1.8 billion light-years across. That distance is enormous. To imagine its size, picture the Milky Way galaxy again, which is about 100,000 light-years wide. You could line up about 18,000 Milky Way galaxies side by side, and the chain would still only just match the width of this mysterious cold region. For something that large, even a small temperature difference becomes interesting. The cold spot appears roughly 70 microkelvin cooler than the surrounding background. A microkelvin is 1/1,000,000th of a degree, so the difference is extremely tiny. But in cosmology, even tiny differences can carry important clues. Naturally, scientists began asking questions. Why would one region of the cosmic background radiation be colder than the rest? Was it simply a random fluctuation, or did something physical cause it? At first, some researchers wondered if the cold spot might just be a statistical coincidence. After all, when you examine something as vast as the entire universe, small irregularities are bound to appear. It would be similar to flipping a coin thousands of times. Eventually, you might get a long streak of heads simply by chance. But as astronomers studied the cold spot more carefully, other ideas began to emerge. One possibility involved something called the integrated Sachs-Wolf effect. That name may sound complicated, but the idea behind it can be understood with a simple picture. Imagine a beam of light traveling through space. Along the way, it passes through regions where gravity pulls on it slightly. If the light travels through a massive cluster of galaxies, gravity can affect its energy. Similarly, if the light travels through a large empty region, a cosmic void, the energy of that light can change slightly as well. The cosmic microwave background radiation we observe today has traveled across the universe for nearly 13.8 billion years. During that time, the radiation has passed through countless regions filled with galaxies, clusters, and voids. If a beam of this ancient radiation happened to pass through a particularly large void, it might lose a small amount of energy. That energy loss could make the radiation appear slightly cooler when it reaches us. In other words, a giant empty region of space might leave a cold imprint on the cosmic background radiation. So astronomers began searching the region of the cold spot to see whether an enormous void existed there. And interestingly, some observations suggested that there might indeed be a very large empty region in that direction. If such a void exists, it could stretch for hundreds of millions of light years. That would make it one of the largest structures in the universe, but the story is not completely settled. Some studies suggest that the detected void may not be large enough to fully explain the cold spot. Other researchers still think the cold region could simply be a rare statistical fluctuation. There are even more speculative ideas. Some scientists have wondered whether the cold spot might hint at interactions with other universes in a larger cosmic multiverse. But at the moment, there is no clear evidence for that idea, so the cold spot remains one of the intriguing mysteries of cosmology. A slightly colder patch in the faint glow left over from the birth of the universe. And even though the temperature difference is tiny, it reminds us how sensitive our observations have become. We can now detect temperature variations across the sky, smaller than 1/1,000,000th of a degree. That level of precision allows astronomers to study the universe on scales once thought impossible. But whether the cold spot is caused by a giant void or by something else entirely, it draws attention to the immense structures that exist across the cosmos, vast regions where galaxies are rare and darkness dominates. One of those possible explanations points toward an enormous structure known as the Eridanus supervoid, a region so large that it might influence the ancient radiation still traveling across the universe today. When astronomers noticed the strange cold spot in the cosmic microwave background, they began searching for anything unusual in that direction of the sky. Was there something physically located there that could explain why the radiation appeared slightly colder? As telescopes surveyed that region more carefully, researchers found hints of something remarkable. A vast region of space that seemed to contain far fewer galaxies than expected. This structure became known as the Eridanus supervoid. To understand what makes it unusual, we should first remember what a cosmic void is. Voids are large regions of space where galaxies are scarce. They form because gravity gradually pulls matter away from certain regions toward denser clusters and filaments. Over billions of years, those regions grow emptier and larger. But the Eridanus supervoid appears to be far larger than most typical voids. Estimates suggest it may stretch nearly 1.8 billion light-years across. That number is difficult to grasp. Light, moving at 300,000 kilometers per second, would still take 1.8 billion years to cross the full width of such a region. To make that scale more familiar, imagine again the size of our Milky Way galaxy. The Milky Way spans about 100,000 light-years from edge to edge. Now imagine placing about 18,000 Milky Way galaxies side by side in a straight line. That enormous chain would finally reach the approximate width of the Eridanus supervoid. It is one of the largest known structures in the universe. Inside this immense region, galaxies are extremely sparse. Instead of large clusters and bright structures, there are long stretches where almost nothing appears. If you could travel through this area in a spaceship, you might drift for millions of years without seeing another galaxy nearby. Most of what you would encounter would be darkness, a few scattered atoms, the faint glow of ancient radiation, and the quiet background temperature of the universe, hovering around 2.7 Kelvin, or roughly minus 270 degrees Celsius. But how could such a huge empty region affect the temperature of radiation traveling through it? The explanation again involves the behavior of light passing through gravity. Imagine rolling a ball down a gentle hill. As the ball moves downhill, it speeds up. If it then climbs the other side, it slows down again. Light traveling through the universe can experience something similar when passing through regions of gravity. In dense clusters of galaxies, gravity pulls strongly on passing radiation. But inside enormous voids, gravity behaves differently. Because there is so little matter there, the gravitational pull is weaker. As cosmic background radiation travels through such a void, it may lose a small amount of energy. When that radiation eventually reaches Earth, it can appear slightly cooler. This effect is subtle. The temperature difference involved is only a few microkelvin, which means a few millionths of a degree. Yet modern instruments are sensitive enough to detect changes that small. So the idea emerged that the cold spot might simply be the result of background radiation passing through a giant cosmic void, like the Eridanus supervoid. However, the mystery is not fully solved. Some astronomers believe the observed void might not be quite large enough to explain the entire temperature drop. Others think several overlapping voids could contribute to the effect, and some researchers still suspect the cold spot may simply be an extremely rare random fluctuation in the cosmic background radiation. In science, it is common for questions like this to remain open for years, while new observations slowly improve our understanding. But whether the Eridanus supervoid fully explains the cold spot or not, it highlights something fascinating about the universe. Space is not uniform. It contains enormous structures that stretch across hundreds of millions or even billions of light years. Clusters of galaxies gather together in bright regions, and between them lie huge bubbles of emptiness, where matter is scarce. These voids represent some of the quietest places in the cosmos, places where the cold background temperature of the universe dominates. But even inside these vast structures, astronomers continue discovering new extremes of cold. In fact, certain clouds of gas within our galaxy have been measured at temperatures just a few degrees above absolute zero, making them some of the coldest gas ever detected anywhere in space. Across the universe, many places are extremely cold. We've seen frozen worlds in the outer solar system. We've explored distant molecular clouds where temperatures drop close to absolute zero. We've even visited giant cosmic voids where the faint background radiation of the universe sets the temperature. But in some regions of space, gas becomes even colder than you might expect. Astronomers have discovered clouds of gas where temperatures fall to only a few degrees above absolute zero. That means the atoms inside those clouds are moving incredibly slowly. To understand how unusual this is, it helps to remember what temperature means. Temperature is really a measure of motion. Warm objects have atoms and molecules moving quickly. They vibrate, spin, and collide with each other all the time. Cold objects have particles that move much more slowly, and when temperatures approach absolute zero, that motion becomes extremely gentle. Inside certain interstellar clouds, scientists have measured gas temperatures around 5 Kelvin. That's about minus 268 degrees Celsius. To picture how cold that is, imagine again the coldest environment ever recorded on Earth. In Antarctica, temperatures have reached about minus 89 degrees Celsius. Now imagine a place nearly 3 times colder than that. That's the environment inside some of these gas clouds. But what makes these clouds especially interesting is that they are still made of gas. On Earth, gases usually spread out and mix with warmer surroundings. Cold gases often warm quickly because they absorb energy from the environment around them. In deep space, however, the environment itself is extremely cold. There is very little energy available to warm the gas, and because space is so empty, the gas particles rarely collide with anything that could transfer heat. The result is a calm, quiet cloud where atoms drift slowly through darkness. One famous example of such a cloud is known as the Rho-Ophiuchi molecular cloud complex. This region lies about 460 light-years from Earth. That distance may sound enormous, but in astronomical terms, it is actually relatively nearby. Light from that cloud takes 460 years to reach us. If the cloud was suddenly to disappear today, people on Earth would not notice until the year 2486. Inside this region, astronomers have measured temperatures around 10 Kelvin, or slightly lower in certain dense pockets. But in some particularly shielded areas of interstellar space, temperatures can dip even closer to 5 Kelvin. These environments are so cold that chemical reactions slow dramatically. Atoms drift through the cloud like snowflakes falling gently through still air. Dust grains coated with frozen molecules move quietly among them. The entire region becomes a kind of slow-motion laboratory for chemistry. The reason these clouds can become so cold has a lot to do with shielding. Earlier we talked about how dust grains inside molecular clouds block much of the radiation coming from nearby stars. That shielding prevents external heat from entering the cloud. It's a bit like being deep inside a thick forest on a cloudy winter day. The tree canopy blocks sunlight, allowing the ground below to remain cooler than the open field nearby. In molecular clouds, dust performs a similar role. The interior becomes dark and protected. Without incoming radiation, the gas loses energy by emitting faint infrared light. Over time, the temperature drops lower and lower. Another interesting factor is the presence of certain molecules that help the gas cool. For example, molecules like carbon monoxide can release energy through radiation very efficiently. When they emit this energy, they carry heat away from the gas. This allows the cloud to cool further. Imagine opening the door of a warm room on a cold winter night. Heat escapes outside, gradually lowering the temperature inside the room. Molecules like carbon monoxide act as tiny escape routes for energy inside these clouds. They help the gas release its heat into space. Eventually, the temperature settles just a few degrees above absolute zero. In these conditions, atoms move so slowly that the behavior of matter begins to feel very unusual. Particles drift quietly instead of colliding violently. Chemical reactions occur gently over long periods, and gravity slowly gathers the gas into denser pockets that may eventually form new stars. These cold clouds remind us that the universe contains environments far beyond our everyday experience, places where matter moves at a near standstill, where heat becomes scarce, and where the temperature approaches the deepest cold that nature allows. But this leads to an important question. We've mentioned absolute zero several times now. It represents the ultimate limit of cold in the universe. But what exactly is absolute zero? And why does physics treat it as such an important boundary for temperature? Throughout this journey, we have often mentioned a special number, a temperature that appears again and again when we talk about the coldest places in the universe. That number is absolute zero. Absolute zero is considered the lowest possible temperature that anything can reach. On the Kelvin scale, it is written as 0 Kelvin. On the Celsius scale, it is minus 273.15 degrees Celsius. To understand how cold that is, let's imagine a simple thermometer. On a typical thermometer used for weather, temperatures might range from around 40 degrees Celsius on a hot summer day, down to minus 20 degrees Celsius or minus 30 degrees Celsius during a harsh winter. Even those extremes represent only a small section of the full temperature scale used in physics. Absolute zero sits far below them. If the freezing point of water is one step down a staircase, absolute zero would be 273 steps below that. That's an enormous drop, and there is a reason scientists treat this point as special. At absolute zero, the motion of atoms reaches its lowest possible level. Earlier, we talked about how temperature measures how quickly atoms and molecules move. Warm objects have particles that move quickly. Cold objects have particles that move slowly. But no matter how much energy you remove from a substance, the motion of its atoms can never completely disappear. Quantum physics tells us that particles always retain a tiny amount of motion. Still, absolute zero represents the point where this motion becomes as small as physically possible. You can imagine it like a room full of bouncing balls. At high temperatures, the balls bounce wildly around the room, colliding with walls and each other. As the temperature drops, the bouncing slows down. Eventually, the balls move so slowly that they barely drift at all. Absolute zero is the point where the motion becomes almost perfectly still, not completely frozen, but as close as the laws of physics allow. This extreme limit of cold leads to some fascinating behaviors in matter. For example, certain materials begin to behave in unusual ways when they approach extremely low temperatures. One well-known example is superconductivity. In some materials cooled close to absolute zero, electrical resistance disappears completely. Normally, when electricity flows through a wire, some energy is lost as heat. But in a superconducting material, electricity can flow without losing energy. Imagine pushing a toy car across a rough floor. The car slows down because friction resists its motion. Now imagine pushing the same car across perfectly smooth ice. It would slide much farther with almost no resistance. Superconductors behave like that smooth ice for electric currents. Another strange effect that appears near absolute zero is called superfluidity. Certain liquids, such as helium cooled to extremely low temperatures, begin to flow with almost no friction. A superfluid can even climb up the sides of a container and spill over the edge. This behavior looks almost magical, but it is simply the result of quantum effects becoming noticeable when atoms move extremely slowly. These unusual properties show how dramatically matter can change in the deepest cold. But even though absolute zero represents the lowest possible temperature, reaching it exactly is believed to be impossible. This idea is connected to a principle in physics known as the third law of thermodynamics. In simple terms, the law says that removing the final tiny bit of energy from a system becomes harder and harder as temperature approaches absolute zero. Imagine trying to stop a spinning top. At first, it slows down quickly, but as it spins more slowly, removing that last little bit of motion becomes more difficult. You might need increasingly delicate touches to slow it further. Similarly, cooling an object becomes more and more difficult the closer you get to absolute zero. Every step requires removing smaller and smaller amounts of energy, and reaching exactly zero would require removing every possible trace of thermal motion, which physics suggests cannot be done. Even the coldest natural places we've explored, the Boomerang Nebula, molecular clouds, cosmic voids, still remain slightly above absolute zero. They may come within a few degrees of that limit, but they never quite reach it. Still, scientists have managed to come surprisingly close in laboratory experiments here on Earth. Using advanced techniques and carefully controlled equipment, researchers have cooled small collections of atoms to temperatures far colder than those found in most of space. In fact, some of the coldest temperatures ever measured in the entire universe were created inside laboratories on our own planet, which raises an interesting thought. Even though space is unimaginably cold, humans have managed to create environments that are colder still. Absolute zero sits at the very bottom of the temperature scale. It represents the coldest possible state that matter can approach. But a natural question appears once we understand this idea. If absolute zero exists as a number, can anything in the universe actually reach it? Could there be a place somewhere in the cosmos where temperature truly drops all the way to 0 Kelvin? The short answer is no. According to everything we currently understand about physics, reaching absolute zero exactly is impossible. Objects can come extremely close. They can approach it. They can get within a fraction of a degree, but they cannot fully arrive there. To understand why, imagine trying to remove energy from something step by step. Think about cooling a cup of tea. At first, the tea loses heat quickly. Steam rises. The liquid cools noticeably within minutes. But as the tea becomes closer to room temperature, the cooling slows down. Eventually, the tea reaches the same temperature as the air around it. At that point, it stops cooling further. Now imagine trying to push that idea much further. Instead of cooling tea from hot to warm, you are cooling atoms that are already extremely cold. Each step towards absolute zero requires removing smaller and smaller amounts of energy, and each step becomes more difficult than the last. It's a bit like walking toward the horizon. No matter how far you travel, the horizon always remains ahead of you. You can get closer and closer, but you never quite reach it. Temperature behaves in a similar way near absolute zero. The closer you get, the harder it becomes to remove the final traces of motion from the particles. This idea is part of a rule in physics known as the third law of thermodynamics. The law states that absolute zero cannot be reached through any finite number of physical processes. In simpler terms, no matter how clever the cooling method is, there will always be a tiny amount of energy left. Particles will always retain a small amount of motion. Even in the coldest known environments in the universe, atoms are not completely still. They continue to move ever so slightly. That tiny motion is unavoidable. You might wonder whether empty space itself could reach absolute zero. After all, space is incredibly cold. Many regions settle around 2.7 Kelvin, which is already extremely close to the limit. But even there, the faint radiation left over from the early universe keeps the temperature from dropping further. That radiation, the cosmic microwave background, acts like a gentle warmth that fills all of space. No matter where you travel in the universe, that faint glow remains. It prevents the temperature from falling all the way to absolute zero. Even the coldest natural object we discussed earlier, the Boomerang Nebula, only reaches about 1 Kelvin. That is incredibly cold, but it is still 1 degree above the ultimate limit. And even if something could somehow cool further, quantum physics tells us that particles would still retain a tiny amount of energy, known as zero-point energy. This energy comes from the basic rules that govern the behavior of particles at very small scales. It means that even when atoms appear almost perfectly still, they still possess a faint trace of motion. You can imagine it like a violin string that never becomes completely silent. Even after the music stops, the string might still carry a faint vibration. Similarly, atoms can never lose every last trace of motion. There will always be a small amount left. Because of this, absolute zero remains more like a boundary than a reachable destination. It is the edge of the temperature scale, a limit that nature can approach but never fully cross. Yet humans have managed to come astonishingly close to that limit. Using advanced technology, scientists have cooled tiny groups of atoms to temperatures only a few billionths of a degree above absolute zero. To imagine that level of cold, think about the difference between freezing water at 0 degrees Celsius and the coldest winter temperature on Earth, around -90 degrees Celsius. Now imagine continuing downward, not just another 100 degrees, but hundreds of billions of times smaller steps. That is the scale scientists are working with when they approach absolute zero in laboratories. These experiments reveal fascinating behaviors. In matter, atoms can slow down so much that they begin to act more like waves than particles. Entire groups of atoms can move together in perfect harmony, forming unusual states of matter. But even in those extraordinary conditions, absolute zero itself remains just out of reach, a final step that physics does not allow us to take. And the fact that we have come so close in laboratories leads to another remarkable story, because the coldest temperatures ever measured anywhere in the universe were not found in deep space. They were created right here on Earth. The universe contains many incredibly cold places: frozen moons drifting around distant planets, dark molecular clouds where atoms move slowly through space, even the strange Boomerang Nebula, where gas cooled to about 1 Kelvin, only a single degree above absolute zero. But something surprising appears when scientists compare those natural temperatures with what humans have created in laboratories. The coldest temperatures ever measured in the universe were actually produced here on Earth. Not in space, not inside a nebula, but inside carefully controlled laboratory experiments. Scientists have managed to cool small groups of atoms to temperatures only a few billionths of a degree above absolute zero. To understand how astonishing that is, let's picture the temperature scale again. Water freezes at 0 degrees Celsius. Absolute zero sits at -273.15 degrees Celsius. The coldest natural places in space, like molecular clouds, usually stay around 10 Kelvin, which is about -263 degrees Celsius. That already feels incredibly close to absolute zero. But laboratory experiments have gone much further. Some experiments have cooled atoms to 1/1000th of a Kelvin degree above absolute zero. If we tried to compare that to everyday temperatures, the difference would be enormous. Imagine the temperature difference between a warm summer day and the freezing point of water. Now imagine dividing that difference into 1 billion tiny steps. Scientists are working within one of those incredibly tiny steps near the bottom of the scale. It's like standing at the edge of a vast staircase and being only a single grain of sand away from the final step. How do researchers achieve something like this? It requires a series of clever techniques designed to remove energy from atoms. One of the most important methods is called laser cooling. That might sound strange at first. Lasers are usually associated with cutting metal or producing bright beams of light. So how can lasers make something colder? The answer comes from the way light interacts with atoms. When a photon of light hits an atom, it can transfer a tiny bit of momentum. In other words, the light can gently push the atom. Scientists take advantage of this effect by shining lasers in very precise directions around a small cloud of atoms. These lasers are tuned so that atoms moving toward the light absorb photons more often than atoms moving away. Every time an atom absorbs one of those photons, it receives a tiny push in the opposite direction of its motion. This gradually slows the atoms down. And as we discussed earlier, slowing atomic motion means lowering temperature. You can imagine it like trying to slow down a group of rolling marbles on a table. If you gently tap each marble in the opposite direction of its movement, the marbles eventually stop rolling. Laser cooling does something similar to atoms. The atoms gradually lose their motion and settle into an extremely cold state. After this step, scientists often use another method called evaporative cooling. The idea is similar to how a cup of coffee cools when steam escapes from the surface. The fastest moving molecules leave first. That removes energy from the remaining liquid, making it cooler. In laboratory experiments, researchers allow the most energetic atoms to escape from a trap. The atoms left behind have lower average energy. Their temperature drops further. By repeating this process carefully, scientists can push temperatures closer and closer to absolute zero. At these extreme temperatures, something fascinating happens. Atoms begin to behave in ways that are very different from everyday matter. One remarkable state that appears is called a Bose-Einstein condensate. In this state, atoms lose their individual identities and begin behaving like a single unified wave. Instead of billions of particles moving independently, they act as if they are one giant quantum object. Imagine a crowd of people walking randomly across a plaza. Everyone moves in different directions at different speeds. Now imagine that entire crowd suddenly moving together in perfect synchronization, like dancers following the same rhythm. That's a rough way to picture what happens in a Bose-Einstein condensate. Atoms begin moving together as one collective system. This strange state of matter only appears at temperatures extremely close to absolute zero. Experiments with these ultra-cold atoms help scientists study the fundamental laws of physics. They reveal how matter behaves when energy becomes almost non-existent, and they allow researchers to test ideas about quantum mechanics that are impossible to observe at normal temperatures. It's remarkable to think about. While the universe itself contains vast regions of deep cold, human technology has managed to create conditions even colder. Tiny islands of extreme cold inside laboratory chambers, colder than most natural environments found among the stars. But even these incredible achievements bring us back to a deeper question. What actually happens to matter when temperatures fall to such extreme levels? How do atoms behave when their motion slows almost to a standstill? And what would matter look like if it existed in the deepest cold the universe can offer? When matter becomes extremely cold, its behavior begins to change in fascinating ways. Most of us are used to seeing matter behave in familiar forms, Water flows as a liquid. Air moves freely as a gas. Metal objects feel solid and stable, but all of these familiar states depend on the motion of atoms. Temperature controls how fast those atoms move. When temperatures are high, atoms vibrate and move quickly. When temperatures fall, their motion slows. And when temperatures approach the deepest cold of the universe, the movement of atoms becomes incredibly gentle. To picture this, imagine a crowded playground during recess. Children run in all directions. They bump into each other, laugh, and move constantly. Now imagine that playground late at night. The swings hang still. The slides are quiet. No one is running or shouting. Everything feels calm and nearly motionless. The playground itself hasn't changed, but the motion inside it has slowed dramatically. Atoms behave in a similar way as temperatures drop. At normal temperatures, atoms vibrate and collide constantly. But as the environment becomes colder, their movement slows. In extremely cold conditions, just a few degrees above absolute zero, the motion becomes almost silent. Atoms still move slightly, but the activity is very gentle. This slowing of motion has important effects on how matter behaves. For example, gases can become liquids, liquids can become solids, and, in extreme cold, even gases that normally float freely in the air can freeze into solid materials. Earlier we mentioned substances like methane, ammonia, and nitrogen freezing in the cold environments of the outer solar system. On Earth, nitrogen makes up about 78% of the air we breathe. But if the temperature dropped below -210 degrees Celsius, nitrogen gas would freeze into a solid. Imagine the air around you slowly turning into a layer of frost. That gives a sense of how dramatically matter can change in extreme cold. In deep space, this process happens naturally. On distant icy worlds, substances we think of as gases can form frozen landscapes. Nitrogen frost can cover the ground. Methane ice can form solid hills and plains. Even carbon monoxide can exist as frozen crystals in certain environments. Another interesting effect of extreme cold involves the structure of solid materials. When atoms move less, they often settle into more orderly patterns. This creates crystal structures that can become very stable. Think about how snowflakes form. Each snowflake grows into a delicate pattern because water molecules arrange themselves in an orderly structure as they freeze. In deep cosmic cold, similar crystal structures can form in many substances. Frozen gases and molecules can arrange themselves into repeating patterns across the surface of icy worlds. But extreme cold does more than simply freeze things. It can also reveal unusual behaviors that do not appear at warmer temperatures. Earlier, we talked about superconductivity and superfluidity, two strange states of matter that appear when temperatures become extremely low. In superconductors, electricity flows without resistance. In superfluids, liquids move without friction. These effects happen because atoms begin behaving according to the strange rules of quantum mechanics. At normal temperatures, the motion of atoms hides these quantum effects. The constant movement of particles creates noise and randomness. But when the motion slows enough, the underlying quantum behavior becomes easier to observe. It's a bit like trying to see the reflection of the moon on the surface of a lake. If the water is rough and full of waves, the reflection becomes blurry. But if the water becomes perfectly still, the reflection appears clear and sharp. Extreme cold creates that calm surface for atoms. The noise of thermal motion fades away, and the deeper patterns of quantum behavior become visible. Even chemical reactions can change dramatically in such conditions. In warm environments, atoms collide frequently and reactions happen quickly. But in deep cosmic cold, atoms move slowly. Reactions may take years, centuries, or even longer. Some molecules that would normally break apart remain stable for long periods. Others form slowly on the surfaces of dust grains or icy particles. This slow chemistry helps create the complex molecules found in molecular clouds and comets. It shows how cold environments can shape the chemical history of the universe. Yet even though extreme cold can slow matter almost to a standstill, it never completely stops atomic motion. Absolute zero remains just out of reach. Particles continue vibrating ever so slightly, following the rules of quantum physics. The universe allows us to approach the deepest cold, but never quite to touch it. And this brings us to a final thought. After exploring frozen nebulae, distant planets, molecular clouds, cosmic voids, and laboratory experiments, a quiet realization begins to emerge. Cold is not rare in the universe. In fact, it is the natural state of the cosmos. Warm places like Earth are the exception. Small islands of warmth in a universe that is mostly dark, empty, and unimaginably cold, of traveling through frozen nebulae, distant planets, dark molecular clouds, and vast cosmic voids, a quiet realization slowly begins to appear. The universe is not mostly warm. It is not filled with glowing stars and comfortable temperatures like the places we know. Instead, the universe is overwhelmingly cold. Warm places, like the surface of Earth, are actually rare. They are small pockets of heat surrounded by an immense ocean of cold darkness. To understand this idea, it helps to think about how the universe is structured. Stars produce heat and light. They shine because nuclear fusion releases enormous amounts of energy in their cores. Planets orbit those stars and receive some of that energy. On Earth, that energy warms the oceans, drives the winds, and allows life to exist. But the region warmed by a star is surprisingly small compared with the vast emptiness surrounding it. Imagine a campfire burning in the middle of a huge frozen plain. If you stand close to the fire, you feel its warmth. But if you walk far enough away, the warmth fades quickly. The cold of the surrounding night returns. Stars work the same way. They warm the space around them, but their influence reaches only so far. Beyond that distance, the natural temperature of the universe takes over again, around 2.7 Kelvin, or roughly minus 270 degrees Celsius. That faint warmth comes from the ancient radiation left over from the early universe. Without it, space might be even colder. But even with that gentle glow, the cosmos remains incredibly cold, and most of the universe is empty space. Galaxies are separated by millions of light years. Between those galaxies lie enormous cosmic voids where very little matter exists. Inside those regions, the darkness stretches across distances that are almost impossible to imagine. If you could travel across one of these voids, you might spend tens of millions of years crossing it even at the speed of light. And during that entire journey, the temperature around you would remain nearly the same, just a few degrees above absolute zero. That idea can feel a little unsettling. The universe is vast beyond anything we experience on Earth, and most of it is silent, dark, and extremely cold. But there is another side to this story. The warmth we experience on Earth is not random. It exists because our planet sits in a very special location. Earth orbits the Sun at just the right distance to receive a steady flow of energy. Too close to the Sun, and the heat would become overwhelming. Too far away, and the oceans would freeze solid. Our planet happens to lie within a narrow region often called the habitable zone. In this zone, temperatures allow liquid water to exist on the surface. That simple condition changes everything. Liquid water allows complex chemistry to occur. It allows molecules to interact and evolve. And over long periods of time, it allows life to emerge. In other words, life on Earth exists because we live on one of those small islands of warmth, a tiny oasis inside a much colder universe. Even within our own solar system, most places remain frozen. The outer planets and their moons experience temperatures far below anything comfortable for life. The Kuiper Belt and Oort Cloud exist in deep freeze. Beyond our solar system, the cold continues across interstellar space. Yet despite this overwhelming cold, the universe still creates pockets of warmth. Stars ignite inside cold molecular clouds. Planets form from disks of gas and dust. Some of those planets orbit at distances where temperatures become mild enough for liquid water. Each of these warm regions is like a small lantern glowing in a frozen night. They may be rare, but they exist. And where warmth exists, complexity can grow. Stars forge new elements in their cores. Supernova explosions scatter those elements across space. New clouds form, and new stars are born again. Over billions of years, this cycle spreads heavier elements throughout galaxies. The atoms in your body, carbon, oxygen, iron, were once forged inside ancient stars. Those atoms traveled across the cold darkness of space before becoming part of Earth. So even though the universe is mostly cold and empty, it also creates the conditions needed for life and light to appear. Cold provides the quiet background where stars can form. Cold preserves the molecular clouds that eventually collapse into new solar systems. Cold slows chemical reactions enough for delicate molecules to survive. In a way, the cold universe is like a vast stage. Most of the stage is dark and silent, but here and there, small lights appear. Stars, planets, possibly living worlds. And on one of those worlds, a species has begun looking outward, trying to understand the enormous frozen cosmos around it. When we gaze into the night sky, we are looking into that cold ocean of space. Yet the warmth of our sun, the air around us, and the life on this planet remind us of something remarkable. In a universe that is mostly cold and dark, we live on one of the rare warm islands where curiosity can exist.